Okay, we're going to continue on here, wrap up chapter 9, roll into chapter 10. I think that's what comes next. Last time we talked about still solutions. And we talked about some common concentration units of solutions, molarity, which is our moles per liter. Remember that you can kind of use this as a conversion, like a formula, really. You can solve for any of those things. Liters would equal moles divided by molarity, and moles, which is a common one, is liters times molarity. So any one of those three things are commonly used in molarity calculations. Remember that when you are given a number with the big M that does stand for molarity, when you are doing a calculation, it is oftentimes best to convert this into a conversion factor, really, and use it like a conversion factor so you don't miss out on any of the units. Again, very common, people just like forget all about the liters part of it. So this means that there is 4.50 moles per liter. Number always stays with the moles part, always 1 liter. Or if you need to flip it around, liters on top, 4.5 moles on the bottom. So if you're doing some type of calculation, I would highly recommend that you do kind of get rid of the big M, use it like a conversion factor, and do some dimensional analysis. Remember that if you are looking for moles and you're using molarity by itself, you do need to make sure that the volume is in liters. So once again, that's 1,000 milliliters is a liter, and that's a common sort of conversion that you use with molarity. Also, very commonly, you're given things in grams. So the use of the molar mass from the periodic table to convert those grams into moles is also a very common sort of conversion that you need to use when you're using molarity. We talked about dilution, and dilution is basically when you add more solvent, which a lot of times is water, to your solution. And because really molarity is moles of solute over liters of solution is really what it is. When you add more solvent and do a dilution, you're really increasing the bottom number here. The result of that is the molarity will go down. So the concentration gets lower because you have a lot more solvent than you did to begin with. So you see the molarity go down. There is an equation that we use for dilutions, which is M1V1 equals M2V2. And that is molarity times volume equals molarity times volume. Typically, the ones are the more concentrated solutions, and the kind of twos are really the more dilute solution. And remember, a lot of times in dilution problems, they want to know like how much water you add. So very commonly, the volume of water is really the difference between the two volumes. Usually V2, again, is your final volume, and kind of V1 is how much of the more concentrated solution you use. There is, as we'd also talked about, a more generic sort of version of this equation, which is C1V1 equals C2V2, where C is just concentration. And again, most of the time, molarity is that sort of concentration unit that you use, but you really could use any concentration unit like those percent mass to mass or percent mass to volume. You could kind of put them in there as well. So you'll sometimes see that. Remember that if you are using this equation here, if you want to be safe, you can convert the volume to liters, but it will work out okay if you leave both volumes in milliliters. If you're specifically using that equation there on the left, the M1V1 equals M2V2, everything will cancel out correctly. But if you are, again, just doing molarity by itself in a non-dilution situation, you need to convert it to liters. Otherwise, you will have millimoles, and you'll probably be off by a factor of 1,000. So if you just want to be safe in all situations, you can convert the volume to liters, and you'll usually be in the correct unit that you need. But you can definitely, as we talked about, kind of leave it in milliliters in this equation, and everything will work out okay. Any questions on that stuff there? Okay, so I think that's where we left off. So guys, just a little bit more stuff to talk about solutions before we roll into the next one. Some properties of solutions. The semi-permeable membrane is really a membrane that allows certain size particles to pass through and other size particles not to pass through. Kind of like there's holes, like Swiss cheese. You can't really sometimes see them with your naked eye, but it's big enough to allow certain particles really to pass through. And obviously, it will restrict other size particles. I think last week you did the dialysis bag experiment, right? They were so 30 minutes, see what was floating outside the bag type of thing. You looked at that bag, you really can't see the holes, but there are obviously small holes in there. At some point, you pop the bag, I think, at the end. That was the good one because you're almost done at that point, I think. So colloids are much larger than solute particles in solution. These are large molecules like proteins, groups of molecules or ions. Colloids are homogeneous mixtures, which remember means that they do look the same throughout, right? So it all kind of looks the same. They do not separate or settle out. They are small enough to pass through a filter, but too large to get through the membrane. Suspensions, on the other hand, are heterogeneous, non-uniform mixtures that are very different than solutions and colloids. They can be oftentimes seen with your naked eye. They do get trapped by the membrane. They also get trapped by filters. I want to say, was it sand you used last week? Charcoal, one of those two usually. So charcoal was like your suspension. When you put that through the filter paper, it really didn't go through the filter paper, right? It got stuck on it in that situation. So here's a picture of all that. Again, we see our settling out here of our suspension. We see our solution and colloid molecules floating around in solution. Once again, both solution and colloid molecules going through filter paper, like your charcoal there, your suspension got hung up. And obviously, in terms of our dialysis sort of bag or membrane here, allowing only certain size molecules, in this case, really solutions to sort of pass through. So that brings us to sort of osmosis. Osmosis is the basically movement of solvent molecules from an area of lower concentration to an area of higher concentration in an effort really to sort of dilute it down. So for example, if you had like a tube here and you had like a membrane there in the middle, and on one side you had salt water, and on the other side you had just plain water. And what would happen in this situation is the process of osmosis, the water side, the pure water, would actually start flowing into the salt water side in an effort to dilute it, because salt obviously is more concentrated. It has salt dissolved in it. Water by itself has nothing dissolved in it. So the more particles you have dissolved in it, the more concentrated it's going to be. It will continue to really flow to this side until it basically reaches what is known as the osmotic pressure. And that's basically the atmospheric pressure pushing back down on it, preventing it from continuing to flow across the membrane at that point. The osmotic pressure of a solution really depends on the number of particles that are in that solution. Pure water has no osmotic pressure. One way you could look at osmotic pressure is to calculate what is known as the osmolarity, sometimes referred to as the osmol. And it is I times the molarity is how you calculate that. I is really the number of particles there are. So, for example, if you had a 0.25 molar solution of sodium chloride versus a 0.25 molar solution of calcium chloride, in this particular case, if we were to calculate basically the osmolarity of each of these solutions, when we look at sodium chloride, it will break apart into a sodium ion and a chloride ion. And in solution, for every one of the sodium chloride units, you get how many ions in this case? You get 2 ions, right? A sodium and a chloride. That means that is what the I value would equal in this case. The I is basically the number of particles you would get. So if we were to calculate the osmolarity here for this example, for the sodium chloride, we would take 2 times our 0.25 molar, and that is going to give us 0.5 osmolarity here. Now, if we look at our calcium chloride in this case, when we have calcium chloride, when it breaks apart, you get a calcium ion, but you actually get 2 chloride ions in this case, right? That's what the Cl2 means. There's 2 chloride ions floating around. That means that's a grand total of how many ions floating around in that solution? I would equal 3 in this case. There's 2 chlorides and 1 calcium, which if we calculated the osmolarity of this solution, even though it has the same concentration, it would be 0.25 times I. I'll just do it behind it there. Will give us 0.75 osmolarity. The one with the greater osmotic pressure in this case is the calcium chloride solution, even though it has the same molarity, because it will generate more particles into that solution, causing a greater osmotic pressure. So that is one way that you can sort of figure out the osmotic pressure. So osmosis always flows from a lower concentration to a higher concentration. And again, the way you can think about it, like I said, is it's like trying to dilute it down, kind of even out the concentration. You might have heard of reverse osmosis. Reverse osmosis is when you blank the screen. No, let's say open that up. Reverse osmosis is when you apply an external pressure greater than the osmotic pressure. And if I do that, what that's going to do is force everybody back the other way. And if you have a lot of filters and stuff, you could grab out all the stuff you don't want in there, right? And it basically will send back the pure water in this example back to the other side. So reverse osmosis kind of apply the external pressure greater than the atmospheric pressure, and it'll kind of push everybody back the other way. Any questions on that there? All right, so that brings us to three types of solutions, and that is isotonic, hypotonic, and hypertonic solutions. Isotonic solutions exert really the same osmotic pressure as body fluids. They are basically IV fluids, because you don't want to give somebody something in an IV because they probably are not in great shape, perhaps at that point, to really mess them up anymore. So what does that mean? Really, it means that if you have sort of a classic example used most of the time as a red blood cell, and basically if you put a red blood cell into an isotonic solution, because the osmotic pressure inside and outside of the cell are basically equal to each other, you basically get nice and even sort of flow inside and outside the cell. The cell is basically like a membrane, right? It's going to allow certain things to come in and certain things not to come in. So the cell here is acting like basically that semi-pyramidal membrane. And what are isotonic solutions? So typically isotonic solutions are 0.9% mass to volume sodium chloride and about 5% glucose, or sometimes it's referred to as in 0.9% saline solution. Doesn't necessarily have to be sodium chloride, but lots of times is, and 5% glucose is a sugar solution. So these two numbers here are really important. Those are basically your baseline of what an isotonic solution is. Now, if you have a hypotonic solution, hypo means less than. That means that if you put, for example, our same red blood cell here into a hypotonic solution, outside of the cell is less concentrated than inside the cell. So what's going to happen is, based on osmosis, as we were just talking about, right? Osmosis means the water molecules will flow from lower concentration to higher concentration. So what will happen in this case is outside the cell is less concentrated. So it's going to go, I need to like send all my solution into the cell here because it's more concentrated inside the cell. The result of that is not so great, because then the cell is going to start to swell and probably burst, which is known as hemolysis. And that's the flow of, again, all that sort of solvent molecules inside it. Now, basically, if you have anything that's less than 0.9% sodium chloride or less than 5% glucose, that would be considered a hypotonic solution. Hypertonic solution is the opposite. Hyper means greater than. So that is a solution that has a greater osmotic pressure. So if we take our same sad red blood cell here, keep doing things to it. So our red blood cell, and if outside of the cell is a hypertonic solution, that means outside of the cell is actually more concentrated than inside the cell. So once again, based on osmosis, what the cell is going to do is, outside is way more concentrated. I need to like give away all my water basically to the solution and trying to dilute it. So what will happen in this situation is the cell will actually send out all its water and solution to the surrounding solution, again in an effort to sort of dilute it down. The resulting of that is not good for a cell as well. It's going to shrink the cell, and known as basically crenation. So again, if you put it into a really concentrated solution, that is typically what you would see. Any questions on that there? All right, so if we look at that, our isotonic, we have a good donut, right? Everybody flowing in and out. We have our hypotonic solution here, jelly donut that explodes, right? And our hypertonic solution, a donut hole. That's a good way to remember it. Nice donut examples here. All right, so you tell me what will happen here. Will it shrink? Will it will there be okay? If we put a red blood cell into these solutions, we put it into a 2% sodium chloride solution, a 3% glucose solution. We put it into 0.5% sodium chloride, and we put it into 5% glucose, and we put it into good old plain water. All right, take a moment there, decide will it swell, will it shrink, or will it be okay if you put this cell into each of these different types of solutions. Okay, let's take a look. So to help us decide, we want to think about isotonic solutions, as we talked about, which is 0.9% sodium chloride and 5% glucose. So if we look at this one, it is as simple as 2% is higher than 0.9%. So higher would be, this is really a hypertonic solution. And a hypotonic solution means that outside the cell is more concentrated than inside the cell. So all the water is going to basically run out of the cell like we have here, and it's going to shrink in this case. Yeah. Any questions on that one there? 3% glucose, 3% is less than 5%. So that would make this a hypotonic solution. Hypotonic solution means that outside the cell is less concentrated than inside the cell. That is going to make all the water basically run into the cell and start to swell it and probably burst in this case, which is shrinking and known as hemolysis. 0.5% sodium chloride, 0.5% is higher than 0.9%. So once again, this would be a hypertonic solution. And once again, in this case, that means outside of the cell is more concentrated than inside the cell. It's going to cause all the solution in the cell basically to run out of the cell in an effort to dilute it. And we're going to see it start to shrink. Any question on those three there? Yeah. Yeah, I will do that a little bit. Yeah. So it's like a very delicate sort of balance that, you know, just a little bit is enough to make it start to flow out of the cell. 0.8%, it would start yeah, so just a little bit under 0.9-ish% in that ballpark, you'll start seeing water start to flow. There's obviously degrees of it. Obviously, if you had something that was super lower or is really super higher, you know, it's going to probably flow out a lot quicker. But you would start to see it's coming out. It's kind of like opening the tap, if you will. So even if you open the tap a little bit, right, it's going to start to flow some water out, right? Other questions? Okay. 5% glucose is right there. That is isotonic, which means really nothing's going to happen here. So you're really going to have even flow in and out of the cell. So everybody will be okay in this case. How about pure water? What will happen? Everybody be okay? Yeah, pure water has nothing in it, which means it has no osmotic pressure. So this is actually hypotonic, actually, a case where maybe water is not a good idea. So this means that really outside of the cell is going to be less concentrated, and inside the cell, that's going to cause water to really flow into the cell and cause it to start to swell in this case. Yeah. Any questions on any of those there? So remember, again, really the osmotic pressure is basically based on how many particles as you got floating around in that solution. So the more particles, the more osmotic pressure that you have. And again, that's why something like pure water has really nothing floating around in there other than water. So it doesn't have any osmotic pressure. All right, any question on hyper, isotonic solutions? All right, Lassi dialysis is a similar process to osmosis as you kind of did in last week's experiment. Again, you can use a dialysis bag, and it really has small holes that allow certain size particles really to sort of flow in and out. In a laboratory, sometimes you're want to use something like a dialysis bag to, for example, get things to the right pH or get it in the right environment. So you can put like your proteins in a dialysis bag and put it into a solution and let it kind of equilibrate. So the environment's very similar to what might be in the body. Our body, right, uses our kidneys and other things to sort of flush out things, right, and do sort of dialysis of products in our actual body. Here is pretty much what you did last week, I think. Yes, at some point you punctured the bag to see what stayed in there, and obviously what stayed in there was too large to fly through. All right, so I think that wraps up this chapter here. Up here with chapter 10, which is acid and bases, also the very last chapter before we venture into organicness and organic chemistry coming around the corner. Here we go. Oh, I'm looking forward myself, I see. All right, so acids have a sour taste. They can cause color changes in paper, which is sometimes known as litmus paper. If you have litmus paper, it basically turns blue. I'm sorry, it turns red. It's acidic. It also reacts with metals in a reaction we talked about, which is like a single replacement reaction. Take a little bit of zinc, some hydrochloric acid, and it will do a single replacement there, and we will get some zinc chloride and some hydrogen gas. And you probably have done this along the way. You usually will see bubbles being generated in this reaction, and those bubbles that you see in the test tube are the hydrogen gas being generated. Aqueous acid solutions are strong electrolytes, which means they do conduct electricity. Bases, on the other hand, have a bitter taste. Obviously, don't taste any acid or bases in the lab. They do feel slippery. Most soaps are bases. Drain cleaners, those type of things, you know, are basically bases. Litmus paper bases will turn litmus paper basically to blue. And they also are strong electrolytes. When we talk about acids, just really quickly in terms of naming acids, so you have an idea. When we talk about acids in terms of the naming, it really involves oxygen as to whether or not oxygen is present. If there is no oxygen, the acid is always something called hydro-something-ic acid. So like HCl, there is no oxygen in that one. So this would be hydro, and the missing part is this guy. So that would be hydrochloric acid. HBr, once again, there is no oxygen. So this would be hydrobromic acid. Now, if it does contain oxygen, it basically will contain everybody's favorite thing, one of those polyatomic ions. And if you remember, those polyatomic ions basically end in one of two ways. They either end in ate or ite. And if it does contain oxygen and your polyatomic ion ends in ate, your acid will be something ic acid. So like HNO3. NO3 is nitrate, ATE. This is nitric acid. H2SO4. SO4 is SO4 2-, which is sulfate. This is sulfuric acid. Now, if your polyatomic ion is ending in ite, and it does again contain oxygen in this case, it will be something OUS acid, like HNO2, for example. NO2 is NO2-, which is nitrite, ITE. This would then be nitrous acid. H2SO3. SO3 is SO3 2-, which is sulfite. This will be sulfurous acid. So if it contains oxygen, it does not have hydro in the name. If it does not contain oxygen, those are the only ones that have hydro in the name. And again, if it does have oxygen, it's one of those polyatomic ions. So you could think of it like, you ate too much, you feel icky. That's a good way to kind of remember that's sort of how the acid name should end. By the way, for all acids, the cation, the positive ion, is always H+. So H+ is always the positive cation in all acids. And you can kind of think of acids, even though really they are sharing electrons and they're covalently sort of bonded. You could kind of think of them almost like an ionic sort of situation. Positive guy is the H+, and the negative guy is, whatever the negative guy that bounces it out to 0. So you think of it like an ionic sort of compound. You have to balance it out to 0 if you put a formula. That is why, for example, here with sulfuric acid, because the sulfate is 2-, we need not 1, but we need 2 of those hydrogens again to balance it out to 0, kind of like a normal sort of ionic compound situation. Any questions on that Cliff Note way of naming? All right, so now you can say not this acid thing. Hopefully you can give the right name, hopefully in that case. All right. So what is an acid? So an acid really is a substance that will produce H+ ions in solution. One really important thing when we talk about acid and bases and sort of acid-base chemistry is basically this idea: H+ and what is known as H3O+, which is known as the hydronium ion, is basically the same thing. Yeah. So I personally, most of the time, will use H+, and pretty much anywhere I put H+, you could put H3O+. It's basically the same thing. That goes both in equations and also formulas as well. So there's really interchangeable sort of an acid-base chemistry. They are basically representing the acid part of the solution. So how do you get sort of H+ versus H3O+? For example, if we were taking something like hydrochloric acid, which is a strong acid, in solution, it would 100% break apart into H+ and Cl-, which is why it is a strong acid. You have 100% these ions. But you could write really the breaking apart of this acid like this, and you get H+. You could also, and very commonly in books, they will write this dissociation of this acid in water. And if you do it with water, you will make H3O+ and chloride. So they are equivalent to each other. Really, the only difference is whether or not you kind of put water into your equation or not. Again, I personally use H+ most of the time, but you can use H3O+ as well. Now, there are some strong acids, and sort of a list of strong acids. What we see here, that's hydrochloric acid, nitric acid, sulfuric acid. So this is sort of a list that's a good one to keep in mind. Hydrochloric acid, nitric acid is a strong acid. Sulfuric acid is a strong acid. Perchloric acid is also a strong acid. Hydrobromic acid is a strong acid, and hydroiodic acid is a strong acid. So that's a pretty good list of pretty much all the strong acids that you'll ever come across. Those 6. Pretty much, if it's not one of those 6, it's probably a weak acid. So, these are probably your big 6 of these are definitely strong acids. And they're all really strong electrolytes because, again, what a strong electrolyte is when it goes into solution, as we talked about, it's going to just 100% break apart into ions. So you have no like HCl units still in that solution. So if you had a beaker of hydrochloric acid floating around, you would have nothing but H+ and Cl- basically in that solution. You would have none of the HCl units still together. And that's why it's really a strong acid, because you can generate a lot of free H+ in that solution really, really quickly. And it will have a big effect, as we'll talk about, on the pH of that solution. It will make it acidic because it has a lot more H+ basically floating around freely in that solution. Any questions on that there? Okay. Bases are guys that produce hydroxide in solution. So OH- is sort of the deal for bases. So if you see OH- on the product side of a reaction, it's going to be a base. And it's really the ability to produce free OH minuses floating around in that solution is really the ability of something to be a base. A lot of strong bases are strong electrolytes, which means they also 100% break apart. So if you have something like sodium hydroxide, which is a strong base in solution, it will completely break apart into sodium ions and hydroxide ions. So once again, in this solution, you will generate a lot of hydroxide really, really quickly, and it will make it basic. It will affect the pH and make it basic as well. You would have none of the NaOH units still together. It will completely have broken apart in that particular case. Pretty much group 1 and group 2 on our periodic table. Right around here, coming down to like where potassium is, hang a right and then go down. Any of those guys there with hydroxide in group 1 and 2 on the periodic table are pretty much where our strong bases come from. Things like sodium hydroxide, potassium hydroxide, calcium hydroxide. That's because group 1 is the alkali metals. Group 2 is the alkaline earth metals. The word alkaline means basic. Yeah. So alkaline metals, alkaline earth metals. That is where a lot of strong bases basically come from on the periodic table. Those guys with hydroxide in it. As we'll talk about, not all bases will actually have OH in the formula, but a lot of strong bases definitely have OH in the actual formula itself, like potassium hydroxide or sodium hydroxide. So what do we get when we take a reaction of a strong acid with a strong base? Ultimately, what is happening in that reaction is you're basically making water. So whenever you react a acid with a base or a strong acid with a strong base, you basically get two things. You get water and you get what is referred to as a salt. A salt is an ionic compound. And basically the water comes from the H plus from the acid and the OH minus from the base is basically where these two come from to make the H2O and form water. We talked about this when we talked about different types of reactions. This is under the big umbrella of double displacement reactions. So basically what's happening here is a double displacement reaction. You take your HCl, which is a strong acid, and you take your sodium hydroxide, which is a strong base. That is a positive, negative guy, positive, negative guy. And as we know with double displacement reactions, the two positive guys will switch partners, which means the H and the OH will come together here to make water. And our sodium and our chloride will come together to make sodium chloride. And that is our salt. And obviously this is our water in that case. So acid-base reaction, it's really called the neutralization reaction, as we talked about when we talk about types of reactions, because fundamentally what is happening is you're frankly making water. So they're kind of canceling each other out. You're making H2O, and that is what is being made in this reaction overall, is that reaction of water. So if I took some sulfuric acid, and I react it with potassium hydroxide, which once again is a strong acid, strong base combination. That's a positive, negative, positive, negative. So you should know that you do make salt and water. So what's a good way to do this? Well, frankly, just take the H from the acid, the OH from the base, and that is going to give you water. And then basically put the other two guys together correctly. So that is K plus and SO4 2 minus. That will give me K2SO4 in this case, and a little balancing would be probably good as well. I think I need like a 2 here as well. And this again would give us our water and our salt in this case. So that's kind of the best way to do it. Is you could almost just put your hands over the H and the OH and the acid and the base, and whatever's left is put those guys together correctly, like you would do if you're doing some type of nomenclature problem or a naming type of problem. Any questions on the reactions there? All right. So that is what we see, and ultimately, we're not going to worry about that actually. All right, so we talked about that. Again, here's another example. Here's nitric acid with our potassium hydroxide. So again, that is going to make our water, and these guys going to make our potassium sulfate. These guys here would be our salts in each of these cases, and obviously this would be our water. In most cases, usually your salt will be soluble. Occasionally maybe insoluble, but in most cases it will be a soluble salt that's usually made. All right, so let's talk about some real definitions here of acids and bases. So early sort of work was done by a guy named Arrhenius. He did a lot of work with electrolytes, and he defined an acid as the ability to produce hydrogen ions in solution. Once again, hydrogen ions are H plus and free H plus in the solution. And then base is really something, as we've been talking about, that's able to produce OH minus in solution. Again, these things need to be free from each other, free floating in solution, not really attached to anything. And that is what makes it something an acid or base, the ability basically to produce that. So if we take our hydrogen chloride gas and bubble it through water, we really will get hydrochloric acid. And as I mentioned, if you look at an equation, you see H plus or H3O plus on the product side of that equation is some type of acid sort of happening, or acidic type solution. If you have something that's more basic, you will see hydroxide on the product side of an equation, and that's more of a basic sort of situation that's usually occurring. So if you actually do see some chemical reactions and you see those things, those are big hints as to, what you would predict as being acidic or basic, depending if you see H plus or H3O plus on the product side, it would be acidic. If you see OH minus on the product side, it would be basic in most cases. Now, this was sort of a good definition of an acid and base, but he did a lot of work with bases that did have hydroxide in the actual formula, and not all bases will have hydroxide in the formula. So from there, where we went to is really a more generic sort of definition of acid and bases, and it's one that most people sort of talk about. And it's what's referred to as the Bronsted Lowry definition of an acid and a base. And in the Bronsted Lowry definition, an acid is a proton donor, and a base is a proton acceptor. So an acid is somebody that will give away an H plus, and that's really important to remember. It's not just the hydrogen, but it is the plus charge. So when it loses that H plus, or if somebody gains the H plus, it will have an effect on the overall charge of each of those things. And sometimes people get the H part, but forget about the charge sort of adjusts as well. We call it H plus a proton because hydrogen has one proton, right? One electron and no neutrons. So the only way you become positively charged is you lose an electron, which in this case would leave hydrogen just a proton. So H plus is referred to as a proton because of that. And again, H plus, H3O plus, really the kind of same situation. So if we look at something, say, like this reaction here, where HA is just an acid, and in this case, water is going to act as the base. So what's going to happen in this case is the acid's going to send the H plus over to the water. When it sends the H plus over to the water, the acid is left with just an A minus. So if you take the H off of HA, you got one less H. And because it was neutral, whenever you lose a positive charge, you then become one more negative. So that's how it becomes A minus. The water will accept the hydrogen, which will make H3O, and also the charges change as well, which will be a plus in this case. The consequence of the Bronsted Lowry definition of acid and bases is it actually creates pairs of things that are related to each other. The acid on the left-hand side of the arrow is related to this guy on the right-hand side of the arrow, and this is what is known as the conjugate base. While the water on the left-hand side of the arrow which is the base, is related to, in this case, the H3O plus on the right-hand side. And on the right-hand side, this is what is known as the conjugate acid. These are sometimes referred to as conjugate acid-base pairs. The absolute only difference between a Bronsted Lowry acid conjugate base pair can only be this guy right here, the 1H plus difference. So if it's anything that is more than 1H plus difference between two things, if you're trying to decide are they pairs with each other, they are not going to be pairs. So the absolute only difference there could be between those two things is 1H plus. And that's what we see if we look at the acid to the conjugate base here. It has one less H plus because it gave it away. And if we look at the water, which is the base to its conjugate acid, it has one more H plus because it accepted it. So that is the only difference that it could be. So for example, if you took something like NH3 here and you react it with some water and you make a little NH4 plus and OH minus in this case. All right, which one donated the H plus in this case? On the left-hand side, which one gave away the H plus, if you had to guess? It is the water in this case, gave away the H plus here, right? Because when water gives away the H plus, it will end up as OH minus. And when NH3 gains the H plus, you add one more H to that, you got NH4, and a plus gives you NH4 plus. So in this case, because the water donated the H plus, that means the water here is our acid, and NH3 in this case gained the H plus, which means it is our base. That means that on this right-hand side here, the NH4 plus would be our conjugate acid, and the OH minus would be our conjugate base, right? So these two things are related to each other, right? The NH3 and the NH4 plus. The only difference between those two things, once again, is just an H plus, and the water here and the OH minus are also related to each other. Once again, the only difference there is an H plus. Now, this brings up an important sort of concept. In the top reaction, the water was the acid. Bottom reaction, the water was the base. There are things, and water is one of those that can act as an acid or a base. And those things are what are referred to as being amphoteric. So if you have what is referred to as an amphoteric substance, that is somebody that could act both as an acid or a base. And water, again, is an example of that. In certain situations, it could be an acid. In other situations, it can be a base. And again, the only difference between those two things are 1H plus difference. You always find your regular acid and bases on the reactant side, left-hand side of the arrow. Your conjugate partners, conjugate bases, conjugate acids, always found on the right-hand side of the arrow. Yeah, so conjugate partners on the right-hand side, our product side, regular old acid and bases on the left-hand side of it. Any questions on that there? All right. This is sort of what we were just talking about. Looking here with our water, our hydrochloric acid example. This is our acid, and this would be our conjugate base. Again, they are related to each other by one less H plus. This would obviously be our base in this case, and our conjugate acid. Once again, they are related to each other by one more H plus. So again, that one H plus is a really important understanding of the pairs and making sure that, you know, something is a pair or not a pair. Any questions on that there? All right, let's take a look at some of this here, I think maybe. All right. So here's sort of the drawing out of what's happening here. The HCl is going to donate that H plus over. And in this case, we would make H3O plus and our Cl minus, sort of the Lewis structure drawing of what's going on. All right, so take a moment here for each of these, decide whether or not For each of these, decide whether or not each of these are a conjugate acid-base pair or not. Okay, let's take a look. So what you should be looking at is really this deal, H plus. Is the difference basically just one H plus between those two things? So if we look at the first one here, the only difference between these two things is one H plus. Yeah, if you put an H plus onto this guy, you get this guy on the left. If you take it off, you get this guy on the right. So I'm going to say yes to that first one is a pair, as the only difference between the two is an H plus. What about the second one here, HCl and ClO minus? The difference here is an H plus, right? But the other difference is there's an oxygen here, but none here, right? So because it's more than just an H plus difference, not a pair in this case, right? So the absolute only difference it could be is one H plus. We got H2PO4 minus and HPO42 minus. So you could do one of two things. You could either take the H off of the guy that has more. So we'll take an H off here. That leaves me an H, a P, O, and a 4. And when I lose a positive, I become one more negative, which would then turn that guy into a -2. So that looks like a match there, yeah. So that would be a pair in that case. And if we look at the last one here, HNO3, NO3 minus, once again, you could either put the H on the guy on the right if you like. So if you want to put the H plus on the one that has less, if I put an H here, that gives me HNO3, and +1 and -1 equals 0, which means I get the same thing here, right? Which means that is a pair as well. So it looks like only number 2 is not a pair. Any questions on that there? By the way, the one with typically more hydrogens is usually the acid. The one with less hydrogens is usually the base in that pairing. All right, let's take a look at this one here. For each of these, write the conjugate base. If you start with each of these guys, write what the conjugate base would be in this case. Okay, so on this one, again, the idea here is it's really an H plus. The key is, should you put it on or should you take it off? That's the big question. So understanding sort of the Bronsted Lowry relationship that we talked about is really important in this case. So if we have an acid and we have a base, on the other side, we have a conjugate acid and a conjugate base. The relationship is the acid on one side is related to the conjugate base, and the base on one side is related to the conjugate acid. So in this particular case, we're asked to write the conjugate base, which would be this guy, which means if we follow this all the way back to the other side, that means that each of the things that we're looking at is an acid. And the Bronsted Lowry definition of an acid is somebody that will donate an H plus. So that tells us that for each of these, we need to actually take off the H plus here. So that's what we should do. So on the first one, we're going to remove an H, which will leave us an H and an S. And in this case, it was neutral, which means when we lose a positive charge, we become one more negative. So that becomes HS minus in this case. Yeah. Question on that. Taking our HS minus, again, we're going to take off the H, which will leave us an S. And it's already started at -1. And when we take off the H plus, we then will become one more negative. So it becomes 2 minus in this case. Yeah. Here, we're going to take off an H. So that will leave us a nitrogen and 2 hydrogens. At the start here, it was neutral, which means when we lose the positive charge there, it will become one more negative. This will be NH2 minus in this case. And lastly, here we will take off one of these hydrogens, which will leave us an H, an S, an O, and a 3. Once again, it was neutral to start with. So when we lose the positive charge there as well, we will also become minus as well. So it's really important to keep track of the charges. And that's something that people really kind of screw up on a lot, is the charge part of it. They sometimes will get the hydrogen right, hopefully, but that charge you gotta watch out for. Question on that. All right, so let's try one more here. If I have HCO3 minus, let's write the conjugate acid for that guy. And then let's write the conjugate base for that guy. In both cases, started with the one in the middle. Okay, we'll start with the conjugate acid first. So if I'm looking for the conjugate acid, that means in this case, going backwards, that is going to act as a base. Definition of a base is it will accept an H+. So going from here to here, we should actually add an H+ to it, and we will end up with H2CO3. As we did in the problem here, if we're going to the conjugate base, once again, the conjugate base is here, which means that would act as an acid in that case, which means we should actually get rid of an H+. And that would give us CO3. And once again, one more negative makes us -2. This is, again, a thing that can act either as an acid or base. So this is amphoteric. A lot of things that could act as an acid or base will have a hydrogen and a negative charge. That's because they have a hydrogen they could give, and they also have that negative charge, which means they could accept it as well. So a lot of those things can go both ways. Any question on Bronsted Lowry conjugate acid base pairs? So. All right, let's talk a little bit about acid strength. If the forward reaction of an acid and base, sometimes what could happen, obviously, is they can't go back the other way. And that is going to represent a weak acid. And a weak acid is like a weak electrolyte. If you remember, weak electrolytes have arrows that head in both directions. An example of this is something like hydrofluoric acid is actually a weak acid. When it breaks apart, it will break apart into H+ and F-. And again, in solution, you actually mainly have this guy still together because it's a weak electrolyte. But you do have some of these ions being produced. And because you have some of the ions being produced, you have some H+ being produced. So it's still considered an acid. It will generate nowhere near the amount of H+ as something like hydrochloric acid would generate, because that is a really strong acid. That's a strong electrolyte. If the forward one predominates, again, you'll have a strong acid, and that would be those lists I put up earlier. And again, in solution, you have none of the whole unit together. They have completely broken apart into ions. And really, in a strong acid situation, they're completely ionized or dissociated, which means you have a beaker full of free H+ basically floating around. In a weak acid, like our hydrofluoric example, you actually have a lot more of the HF guys together, but you do have a little bit of H+ and F- in there. So in a weak acid situation, it does really stay together, the acid, but it does break apart a little bit to produce some of that H+. And that typically will be the guy that would have the reversible arrows that are be part of it. Now, a couple of relationships. If you have a strong acid or even a strong base, its conjugate partner, the conjugate acid or the conjugate base, will be relatively weak. So there's sort of an opposite relationship between the acid and base and its conjugate pair. If it's a strong acid or strong base, its conjugate base or acid will be weak. And if it's a weak acid or weak base, its conjugate partner will be relatively strong. Outside of this class, what could happen is those conjugate partners that are relatively strong could continue to react with water through a reaction known as hydrolysis and really affect the pH of the solution. It can make it more acidic or more basic, depending on sort of what's in that solution. We are our list of strong acids. There are acids which can only give away one H+, like hydrochloric acid. It has one H+, and that is what is referred to as being monoprotic, has one hydrogen to give. Something like sulfuric acid, H2O4, H2SO4, has two hydrogens. That is sometimes what is referred to as being diprotic, because it has those two hydrogens. And there's also triprotic acid, something like phosphoric acid, has three hydrogens to give. That is sometimes referred to as being triprotic. And in each of these cases, H+, and obviously the negative guy has, here the negative guy has a -1 charge, here the sulfate's -2, and here's the phosphate's -3, which is why you have all those hydrogens in that case. Although we don't really talk too much about it in this class, if you do have a diprotic acid or a triprotic acid, the hydrogens actually do come off actually one at a time. So what would happen first is the hydrogen would, for example, if we took sulfuric acid, the first thing that would happen is the first H plus would come off and we would make HSO4 minus. And then the second thing that would happen is the HSO4 minus would lose an H plus and we would make sulfate. Do you think it's easier to remove the first hydrogen or the second hydrogen? It is easier to remove the first hydrogen. It's neutral, right? When you get rid of it, you now have something that's negatively charged. You're trying to pull off something that's positively charged. It gets really, really harder to do. By the way, that is also why when we look at acid conjugate base pairs like we were talking about, H2SO4 and HSO4 minus, those two guys are pairs. They're only one H plus difference. HSO4 minus and SO4 2 minus, those guys are also pairs. If I go from H2SO4 to SO4 2 minus, are those guys pairs? They are not pairs. That is more than two, that's more than one hydrogen. So although they are related to each other in the sense they do come from the same thing, they are not conjugate acid-base pairs because H2SO4 and SO4 2 minus are two hydrogens different. And it's because they do come off one at a time. And that's why these two guys are pairs and these two guys are pairs, but going directly to that end point there does not make them pairs. Any questions on that there? Yeah. All right, so let's talk a little bit about water as an acid and a base. As we've been talking about, water is an amphoteric substance. In certain cases, it could act as an acid. Other cases, it could act as a base. So as we saw in a couple of the earlier reactions, here, water is sending the H plus over, which is acting as an acid. On the bottom one here, water is accepting the H plus, which means it's acting as a base. And frankly, water can react with water. One water is an acid, one water is a base. That is what is going on in solution. So one could donate and one could accept an H plus. And if I did that, that would be my acid and this would be my base in this case. This relationship's important. It sets up what is referred to as an equilibrium in water, basically. And we could write what is referred to as an equilibrium constant for water. And it's an important relationship when we're doing some calculations to determine whether or not a solution is an acid or base. Bless you. And that relationship is what is referred to as Kw. And Kw is the concentration of H plus. And that's what the little bracket means. It means concentration. And really what it means is molarity, moles per liter, of H plus times the concentration of, not H, again, of OH minus equals 1 times 10 to the minus 14. That is what is known as Kw. This is one of the first equations as well. As you can see here, you can use H3O plus instead of H plus, so whichever one you like. Again, I personally use H plus most of the time. The relationship between H plus, which is like the acid part of the solution, and OH minus, which is like the base part of the solution, is they run opposites of each other. So as one goes up, the other goes down, and vice versa. Obviously, as H plus goes down, the concentration of OH minus goes up. So they basically run opposites of each other. And you could use Kw to calculate the concentration of the H plus or OH minus concentration in solution. And you could use it to decide whether or not that solution is acidic, basic, or neutral. And if we look at that there, if we calculate the H plus concentration and it's bigger than the OH minus concentration, so the acid part is larger than the base part, then the solution would be acidic. If we calculate the OH minus, which is the basic part of the solution, and it is larger than the H plus, which is the acid part of the solution, then it's basic. And if they equal each other, they would equal 1 times 10 to the minus 7. and that would be a neutral solution. The good news is, frankly, it is the same calculation, just divided by whatever one they give you. Also, super important, if you've forgotten or don't remember, make sure for sure in this chapter you are using your exponent buttons, or you're going to find yourself way, way off. So a reminder, if you had to put KW, which is a constant, kind of a value that you always have, you would hit 1, you would hit your exponent button, you would hit your negative button, and you would hit 14. Make sure that you get something that looks like this on your calculator. When you put it in, you definitely want to make sure you use your exponent button. You're going to be really, really off in this chapter for sure with all those calculations. All right, so let's take a look at one maybe here. There we go. All right, so for each of these here, I would start with the calculate the H plus or OH minus, and is it acidic, basic, or neutral? Grab your calculator, make sure you know how to punch them in. The good news is they're all the same calculation. So basically take 1 times 10 to the minus 14 divided by either the H plus or 1 times 10 to the minus 14 divided by the OH. Okay, so again, then let's take a look at this first one here. So it really doesn't matter which one they give you. It's really the same calculation using that KW, which you always have. In this case, we have the H plus, which is the acid part of the solution given to us. We would want to solve for the OH minus, which is the basic part of the solution. We take 1 times 10 to the minus 14, which is the value of KW. We would then divide it by what they gave us. So in this case, this would give us 1 times 10 to the minus 14 divided by 3.4 times 10 to the minus 4. Once again, you would go 1 exponent button, negative button 14, a little divide button, 3.4, exponent button, negative button, and 4, and it equals. And if you do all that good stuff, hopefully here, you get a calculator that's not dying like mine, but we'll try it. Maybe I can see it divided by 3.4 to the minus 4. Looks like maybe here, I hope. You end up with 2.9 times 10 to the minus 11. This would be molarity, as the original concentration was also molarity here. First off, any questions on that calculation there? So to determine whether or not it's acidic, basic, or neutral, you want to compare the two concentrations. We want to take the H plus or OH minus concentration and compare it to the H plus concentration. Which one's larger here? The H plus or the OH minus? It is the H plus concentration is larger in this case, and it would be acidic in this case. So just a reminder of a couple of things, bless you. When you have a negative exponent, the smaller negative exponent is the larger number, because to the minus 4 means you're going 4 places this way and putting zeros. To the minus 11 means you're going 11 places this way and putting zeros, which makes it a much smaller number. So when you're comparing negative exponents, the smaller negative exponent is always the larger number. So here the H plus has a smaller negative exponent, which makes it a larger number than the OH minus, which means the acid part of the solution is greater than the base part of the solution. Any questions on that there? All right, we're laid up there